Alright guys, let's do another series parallel circuit here. So usually by the time you guys finish the 18 ones that I do in class, there's always those who ask for additional circuits. Up until this point I haven't taken the time to do some additional circuits, and I'm lazy. So what I did was I just went online, typed in series parallel circuits into the search engine, and I came up with two really good resources. So I'm going to put these in the comment section below. So this circuit that I've grabbed was this one right here. So this kind of dominates that search engine there, and you'll find that this circuit is used time and time again. I believe these guys are the original people who put it out. So Electronics Tutorials, awesome site, and this YouTube video below is really good at breaking down a separate circuit as well. So what I've done is I've just taken this exact same circuit. I have doubled the values everywhere. So I've just taken the same circuit but changed the ratio there. And then if you need an additional circuit, so go to their web page, go through the exact same circuit but with half the values there, and they do a great job of breaking it down slowly. It's actually right here. So they're going to break it down in a different fashion in that they'll show you RA, RB, and they're basically doing series parallel circuits with the same laws that we're going to be doing in this video. Okay. In addition to that, you may want to go to this gentleman's website. Jesse Mason does an awesome video here on how to solve any series and parallel circuit problems. He shows how to break the entire circuit down and then build it back up. You can see that it's almost identical to the circuit that we're going to do as well. So now you've got three different circuits you can work off of from this one video. I will put the links below before I start this. Okay, so back to the circuit that we were looking at earlier. Where do you start here? Well, remember that what you're going to do is you're going to take a look at the circuit and you're going to mark out where each of your parallel nodes are. So wherever you find a parallel node, you can mark it off with a different color. Okay, so what I'm going to do is I'm just going to mark off each of the parallel nodes. So we've got current flowing from the source going out. Let me pause here and just get a different font so that you can actually see where the current is rocking here. Hang on. Okay, so I've decided to go with a 24 volt source, and we'll go from one side of the source, and we're just going to draw in the way that the current is flowing from one side of the source to the other. Now, at this point right here, once it goes through R1, that's a parallel junction right there, because we can see here the current rocks in this direction, and it goes down here towards R2. Let's finish off that circuit here through R2 because it looks like the current goes down here through R2 and then right back to the source. So it looks like that source voltage of 24 volts is going to be across R1 and R2 there. Okay. If we continue along in this direction, then we're going to go through R3. Okay, so this is quite obvious, but we're just going to take the time to show where the parallel nodes are. Okay, and then we've got current that rocks in in four different directions. Looks like current goes through R8 and R10, so we've got a series circuit that we can deal with there. It also goes through R9 here, goes down through R6, and then depending on the way you're looking at it, kind of rocks back here through R4. Okay, excellent. So now we've got all of our currents through each of these other resistors. And let's start on the right-hand side, and we'll just show again the parallel junctions where the current combines. So current is going to combine here, and looks like it's going to come back to the source. It's going to go through R7, recombine with the current from R6. There's another parallel junction where the currents are combining. Then that combined current is going to rock through R5, and the currents that we had going through R4 and R2 and the combination of everything from R5, they're all going to rock together right here so that the current going through R1 and the current coming back is going to be identical. Excellent. Okay, so now we can see which way the currents are flowing from one side of the source to the other, but it's still messed up. I can't make heads or tails of this yet. So what we're going to do is we're going to try and redraw it and see if we can show exactly which ones are series combinations and which ones are parallel. So we'll start with, why don't we start with the outside circuit there, being this current here. It looks like we got a resistor here, R1, R3, R8, R10, R7, and R5. We'll start drawing that guy out, and then we can see where R2, 4, 6, and 9 fit into the mix. Alright guys, so the next thing is just to redraw this to try and figure out where the series and parallel combinations are, because it's not readily apparent in this diagram above. So let's start off by doing R1, R3, R8, R10, R7, and R5. Now I've just drawn all those guys in. I've gone from one side of the circuit back to the other side. There's a million ways to do this, but I'm just going to try this and see how it works out. So let's draw in each of these names here. So we got R1, R3, R8, R10, then we've got R7, and finally R5. So I went from one side of the source to the other side. Now, are these in series? No, they're not exactly in series. And we're going to find that there are parallel combinations that combine with this one. But let's just check off the guys that we've got so far. And we'll see how the rest of the circuit kind of plays into this. Now, maybe we'll start off with R2 now, because if we go from R1 through R2, we can get right back to the source. So I'm just going to arbitrarily drop in R2. Let's drop it in down here a little bit. Okay, and hopefully that leaves us with enough room to throw in the rest of the resistors. Okay, the next thing we got, let's see, we've got all these guys, right, all the way around, and we've now taken care of R2. We can see that R2 is in series with R1. There's a parallel node right here that corresponds to right here. So now what do we need to take care of? Maybe R9. R9 seems to be in parallel with R8 and R10, right? You can see that R9 is right across those two guys. So R9 is going to go across R8 and R10. So let's just drop in a line here, come across here, and then tie into the other end of R10 there. Excellent. Okay, that takes care of this guy. Okay, that looks good. Then what do we need? We need R4. R4 looks like it's going from this parallel junction right here. So the tail end of R3, and then it's going into the tail end of R2. So from tail end of R3 to the tail end of R2. Okay, well, tail end of R3 is right here, right? So we can drop in that resistor, and we need it to line up with the back end of R2. Excellent. Okay, well, let's just bring this straight across, and we can see that 5, 4, and 2 are all tying together to the same spot. Excellent. So this guy is R4. Now all we need to do, we've taken care of this guy here. The last thing we need to do is just bring in R6, and it looks like we've got everything in one diagram. So our last one being R6 looks like it's going from the tail end of R3, and then it's also going into the point between 5 and 7. So tail end of R3 would be right here, and somehow we need to throw in a resistor that would then go to the midpoint between R5 and R7. Well, if I put it here, then I'd have to be jumping over this line here. So maybe we'll draw it up here, drop in that final resistor, and then it has to tie into the midpoint between 5 and 7. And we said that guy was R6. Beautiful. Okay, now we've taken care of all of the resistors in the circuit. Instead of being a confusing diagram like this one above, hopefully this one's a little bit easier to work with. And now we can see where the parallel combinations are. And now we're going to slowly break down placing our source voltage across. And we also have to break it down to our total resistance, because we still don't know our total resistance for the circuit yet. Excellent. All right, guys. So what I've done is I've just taken that diagram we just did, moved it onto a blank sheet here, blown it up a little bit so we can fit in all the values. And I've placed in all the resistance values for each of these resistors now. Okay, in addition to that, maybe we want to throw in our supply voltage at 24 volts. And we can also just make note of where we have these parallel connections, where we've got current going in different directions and then coming back to recombine. Looks good. Another parallel connection here. And then obviously everything's coming back over here, back to the source. Excellent. Okay, so now we got to figure out our total resistance for the entire circuit. So what we're going to do is we're going to slowly break this down into an equivalent circuit by looking for series circuits, break them down, and then do parallel combinations as we go until finally we get our total resistance. Then we'll get our total current, and we can kind of build the circuit back up and move through with our currents for the entire circuit. Okay, so first thing we need to look for is any series combinations. So let's see, we've got R1 and branches off, R3 then branches off, R6 is on its own, 5, 7 are on their own, 9, 4 are on their own, 2 is on its own. The only ones that seem to be directly in series are R8 and R10. So we know that resistors in series are going to add together. R8's 20, R10 is 4. So we'll add those guys up to give us 24 ohms. And we'll just eliminate these guys. So 8 and 10, and we're back down to 24 for an equivalent resistance. Okay, so we'll just draw that in there. Okay, so we have an equivalent resistance for 8 and 10 because we put those two guys together. Okay, next thing we need to do is look for any parallel combination here. So let's see, let's take a look and see if we can find a parallel combination that we can bring together. And we can, seeing as most of them are just two resistors in parallel, we can use product over sum to find the equivalent value. So let's do these guys. Let's do what we did with 8 and 10, the combination of those guys. And let's do the combination of this resistor here and R9. So we've got one value at 24, one value at 12, and those guys you can see are directly in parallel there. So if we're looking for that equivalent resistance, then we're going to have what? 24 times 12 over 24 plus 12. Okay, so we'll do the product over sum there. Let's see, 24 times 12 is 288. And if we divide by that, the addition of the other guys, what do we got? 36. So 288 divided by 36 gives us 8 ohms. Excellent, nice round value. Okay, so this one that we had for 8 and 10 and the combination with 9 is now going to be simplified down to an 8 ohm resistance. So what we're going to do is we're going to take away this guy because we found that equivalent resistance. And we're now going to change this guy to an equivalent resistance of 8 ohms. Yiddy. Okay, now that value is now in series with the 16 ohms. So the next thing we can do is we can combine those guys in series. So we can do R7 and the equivalent value that we had here. So 16 ohms plus the 8 gives us a value of what? 24 ohms, right? So let's eliminate this bad boy right here. We'll draw in our connection here. And now the combination of those resistors is now 24 ohms. Excellent. Okay, let's keep going because now it seems like R6 and this equivalent resistance are now in parallel here. So we can now do the equivalent resistance using product over sum again. We'll do 12 times 24 over 12 plus 24. Okay, the 12 times 24 gives us 288. Well, this looks exactly the same as before, my friends. Okay, then below we got what? 36. 288 divided by 36. There's a trend that's happening. Is 8 ohms. Excellent. Okay, so R6 and our combination resistance right here, the equivalent resistance for those two guys is going to be 8 ohms. So we can now eliminate R6. Okay, and this value right now is 8 ohms. Nice. Okay, that guy is now in series with R5. Okay, so we've broken everything down here to one equivalent resistance of 8 ohms, which is now in series with R5. So now we can eliminate R5, which was 8 ohms, add that on to our equivalent resistance, and now we got 16 ohms for that equivalent resistance value. Nice. Right below that, we've got another 16 ohms. Very nice. Those guys are in parallel. And if we have two values of resistance that are exactly the same, then the equivalent resistance is going to be, in this case, 16 ohms, divided by the number of paths. The number of paths is 2. So again, there's a definite trend to this circuit. I'm liking it. There's 8 ohms of resistance remaining there. So R4 has now been eliminated. Okay, and now we have an equivalent resistance of 8 ohms there. That guy is in series with the 8 ohms for R3. So we're going to eliminate R3 now. This guy is now 16 ohms. Recombine that. And now it's apparent that the 16 ohms is in parallel with R2, which is also at 16 ohms. Go back to this guy. Equivalent resistance is 16 ohms divided by the two paths that are provided, giving us 8 ohms as a equivalent resistance. So now we can eliminate R2. It's done. And we're very close to finding our final answer here. Okay, so we got 8 ohms for equivalent resistance for all the noise that we just eliminated. And the last thing we do is we just combine R1 with our 8 ohms of equivalent resistance, and it looks like our total resistance is going to be 20 ohms. Very nice. Now we've got our total resistance. Now we're rocking. We can use that 24 volts and the 20 ohms in order to find our total current. And let's just draw that in here so that there's no questions. Excellent. So total resistance of 20 ohms, total voltage applied is 24. So now we can find the total current flowing in this circuit. We got 24 volts, we got 20 ohms of equivalent resistance. Excellent. And so 24 divided by 20 gives us 1.2 amps for our total current going in and out of that circuit. Nice. So now what we're going to do is we're going to bring that 1.2 amps and we're going to bring it into our initial drawing. So we're going to build back up to that larger drawing now. If you got lost as to where I came up with that 20 ohms, then just stop the video, go back a little bit, and just slowly walk through how we came up with that 20 ohms of total resistance. Okay, so back to our original diagram. We now know that there's 1.2 amps flowing in this circuit. So we can draw in our 1.2 amps coming from the source and then going back to the source. Excellent. Okay, that 1.2 amps is going to flow now through R1. So we know that through R1 we're going to have 1.2 amps flowing there, and that will provide us with our first voltage. So 1.2 amps coming up here, and that's going through R1. And obviously coming out of there, we're also going to have 1.2 amps. And then let's see, just our current times our resistance, 1.2 times 12 is going to give us a voltage of 14.4 volts across that first resistor. Excellent. Okay, now we got 1.2 amps, and now we got to figure out, let's see, either a voltage or a current. So let's see, we've got R1, and it looks like current goes in two directions. Goes over here to this combination of 3, 6, 8, 10, 7, 5, 9, and 4. And it also comes over here to R2. So it looks like the 24 volts that's from the source is applied to this side of R1, and it's also available over on this side of R2. So the whole source voltage is applied across R1 and R2. So that means that this voltage right here at R2 would be the 24 volts, which we've got for the source, minus the 14.4 volts. So we got 9.6 volts across R2. Very nice. Now we're going to use that voltage and the resistance. We're going to take the 9.6 volts divided by 16 ohms. That gives us 0.6 amps flowing in that portion of the circuit. Okay, well, we had 1.2, we took away 0.6, and that leaves us with 0.6 amps flowing in the remaining portion of the circuit. If you go back a little bit on the video, you would have found that the equivalent resistance of all of this was basically 16, right? It had the same resistance. So same current is going to flow in each of these portions of the circuit. So we got 0.6 amps flowing here, and coming out of that resistor again, the same current. Beauty. So now we got 0.6 amps. We've got to multiply that by 8 ohms, and that gives us 4.8 volts across R3. Okay, so now we can do the same thing. Initially, we used the 24 volts as the supply for R1 and R2 because we have that path right across the 24. Now what we're going to do is we're going to use the R2 with the 9.6 volts as the source because for R3 and R4. If we follow from here, that same voltage should be applied here at one side of R3, and if we follow that voltage, it's also available over here at R4. So the voltage across R3 and R4 should be 9.6. Well, there's 4.8 volts lost across R3, and if we take that 9.6, take away the 4.8 volts, that leaves us with 4.8 volts across R4. Okay, so just like we had in similar circuits and similar videos that we covered before this, you can always use this as the supply for R1 and R2. Then following that, looks like R2 is now the supply voltage that's being applied across R3 and R4. Excellent. So now we've got 4.8 volts and we've got 16 ohms. So we'll take the 4.8 volts, we'll divide it by the 16, and that gives us 0.3 amps that's flowing in this portion of the circuit. Beauty. We're working our way through. We're finding most of the voltages here. Now we just got to take a step back and take a look at the circuit and figure out what our next voltage is going to be, or whether there's the same current flowing in another path. Well, I'll tell you, I've looked at this for quite a while here and messed me up for quite a while trying to find out the next step here. So let's see, this 4.8 volts that's here, that's applied across R9 and across all of this combination here. So we can't really keep going with that same rule that we just had. So maybe the currents are going to help us out. Let's draw in our currents here. So we have 0.6 amps right here. We have 0.3 amps in this rung. We have a combination of 1.2 amps coming back. So let's see, we got 1.2 amps coming back. Looks like we have 0.9 amps for the combination of those other two portions of the circuit. 1.2 minus the 0.9, leaves us with 0.3 amps flowing in this portion of the circuit. So it's not really the voltage at that point that's going to help us out with the rest of the circuit. It looks like the current. Now that current, if we compare it, should be the same as the current on the remaining lines here, which it is. We have 0.6 going into this parallel node, 0.3 coming down here, leaving us with another 0.3 amps that's going to flow through all of these guys and recombine here. But this is awesome because now we know that the current here is 0.3, and that means that the current flowing through R5 is going to be 0.3 amps. Beauty. So now we got 0.3 amps. We're going to multiply that by the 8 ohms, and across this guy we got 2.4 volts. So hopefully that slowly helps us in determining maybe another voltage in the circuit there. Okay, so pause the video again, take a look, see if that helps you out to find another portion of the circuit. It's either the current flow or it's going to be using one of the resistors as a source voltage for the other guys. Let's see, over here we still have all this noise over here, so it's hard for me to see individual current flows there. Maybe we can look at the voltage. Let's use this guy, this 4.8 now, as a source voltage. And that voltage is going to come up here, and it's going to go across R6. And the other side of that 4.8 volts is also going to be apparent right here. So we got 4.8 volts, but we're going to lose 2.4. So that means that the remaining voltage across this guy right here, across R6, is going to be 2.4 volts, because this voltage here has to match with this voltage here. We've lost 2.4, leaving us with the remaining 2.4 volts across R6. Excellent. Okay, that's going to help out now, because now it's going to give us an additional current. We have 2.4 volts. We're going to divide it by the 12 ohms. So we got 0.2 amps flowing in that portion of the circuit. Nice. Now we're just down to 2 rungs there. We have to find voltage values and an equivalent current value. Okay, so we have 0.2 amps flowing here. We have 0.3 amps flowing here. And then we also have another 0.3 coming here. So this 0.3, we lost 0.2 amps. So we need 0.1 amps flowing in this final combination here. So you could look at the current and maybe the total resistance there to help you out. Maybe we'll look at, I can't really see it. Let's maybe look at the voltage across R8, R10, and R7. So this 2.4 volts would be here at this junction. And that 2.4 volts is also across here at this junction. So the 2.4 volts is applied across each of these resistors, R8, R10, and R7. And if we add up R8, R10, and R7, we got, what do we got, 24 plus another 16. That gives us 40 ohms. And if we take the 2.4 divided by that 40 ohms, that's going to give us 0.06 amps flowing in that portion of the circuit. Okay, so now we've got that current. Remember, that current is going to be coming right across, right? That is essentially a series circuit here. So that identical current is going to go right across. And that'll leave us with our voltages there on R8, 10, and 7. So R8 is going to be, 20 ohms times the 0.06 amps. That's going to be 1.2 volts across this guy. Don't need much room to write my voltages there. Okay. Next one, we got 0.06 amps, and we got 4 ohms. So we're going to multiply that by 4. That gives us, is that right? 0.06? Yeah, that's only 0.24 volts across this guy. Nice. And then finally we have 0.06. R7, it is 16 ohms, and that leaves us 0.96. across R7. A quick check is to add up the 1.2 plus the 0.24 plus the 0.96. Beauty, that gives us 2.4 volts. So the combination of all these voltages here for 8, 10, and 7 is matching with this voltage on 6. This diagram is getting pretty messy. Last one here, we need R9. So let's see. We can see that R9 is right across R8 and R10. R8 and R10 have a voltage of 1.2 and 0.24. And if we add those guys up, the remaining voltage is going to be 1.44 volts across R9. Very nice. Okay, so let's see. We had the 0.3 amps that was flowing here. And we're going to subtract the 0.06 amps that we have flowing in this portion of the circuit. And then we're going to subtract the 0.2 amps that's flowing in this portion of the circuit, leaving us with 0.04 So 0.04 amps flowing through R9. Let's just double check if that works. 0.04, right, amps times 12 ohms is giving us 0.48. Man, what did I do there? Okay, so that's no good. That current there and that volt, nothing's working out there with those values. So it must have gone off the mark here. Let's see if we can go back a few steps and see where I went off the mark. I made the assumption that voltage of 2.4 volts was across R8, R10, and R7. That gave me the 0.6 amps. But I didn't take into account, the fact that R9 is in parallel with R10 and R7. So let's go back a little bit. Some of you guys already noticed this. And we're losing it because the values that I was writing down on the page were not matching yours. Just wanted to show you a quick way that you can screw this up. So I thought that the 2.4 volts was right across each of those resistors. Sorry. But in effect it wasn't. So let's take a look one more time and see if we can find those values. Okay, so that 2.4 volts is across here and here, but we have to take into account that these guys are in parallel. So we have the 2.4 volts, but we need to find the equivalent resistance of these guys one more time. So here we have 24 volts in parallel with 12 ohms, right? So again, if we go and do that product over sum, 24 times 12 is 288 divided by 36. That's 8 ohms. So these guys right here are the equivalent of 8 ohms. Plus the 16 is 24. So really it's 2.4 volts across 24 ohms of resistance. Okay, so that leaves us with 2.4 volts divided by 24 ohms of resistance. That gives us 0.1 amp flowing through there. Okay, so the combination of these guys is going to be 0.1 amp there. Well, that makes sense, right? Because we've got 0.2, 0.1 adding to give us the 0.3. All right, things are looking a little bit better. Okay, let's see if it finally works out now. Okay, so we got 0.1 amps flowing there. We're going to multiply that by the 16 ohms for R7. That gives us 1.6 volts across R7. Nice. Okay, so now what's our next step here? We got the current there, we got the voltage across R7. Let's take a step back and see if we can just figure out R8, 9, and 10. Okay, well let's take a look at the voltage. We do have 2.4 volts from here to here, right? So that means that we should have 2.4 volts from the same point down here across to here. So we've got 2.4 volts impressed across R9 and R7. And if we lose that 1.6, then that leaves us with 0.8 volts across R9. Okay, so these two currents, the current through R9 and the currents through 8 and 10, have got a sum to give us 0.1 amps, and then we can finish the sum off. So we have 0.8 volts. We're now going to divide by 12 ohms, and there's 0.0666 repeating here. Okay, so we got 0.067 amps through that portion of the circuit. Okay, so if we have 0.1 amps over here, and we've lost the 0.067 through R9, the remaining current is going to be 0.033 through these guys. All right, so that 0.033 and the 0.067 are going to sum to give us that 0.1, and we can find our last two voltages there. So 0.033 amps times 20 ohms is going to give us 0.66 volts across R8. And then finally the voltage across R10 is going to be 0.033 times the 4 ohms gives us 0.132. Excellent. And if we sum those guys together, the 0.132 and the 0.66, they should sum to give us 0.8.